Okay, welcome to part one of this lecture. And if you can hear the screaming baby in the background, just ignore her. We're really not abusing her, I promise. So last time we finished up looking at a gauge transformation where we transformed some potentials to the Coulomb gauge. Now we're going to be looking at the same potentials, but we're going to transform them into the Lorentz gauge. So we start with our potentials. We have our vector potential A equals some constant f times t x squared x hat, and then our scalar potential v is equal to g x t squared. Okay, so the criteria for the Lorentz gauge is del dot vector potential A prime is equal to minus mu naught epsilon naught dv prime dt. Okay, so that's the Lorentz gauge condition. Okay, so we just plug in the definition of A in terms of, the definition of A prime in terms of A and V prime in terms of V. So we have del dot, so A prime is always going to be A plus the gradient of some function lambda, and is equal to minus mu naught epsilon naught d dt, and then v prime is always equal to v minus the time derivative of that function lambda. Okay, so our job then is to figure out what function of lambda satisfies this. So if we look at the left-hand side, we have del dot a, so we can plug that in. So that's just going to be 2 f t x plus del squared lambda, and this is equal to minus mu naught epsilon naught. Dv dt is going to be times 2g x t, and then we have plus mu naught epsilon naught d squared lambda dt squared. Okay, so we can move all the lambdas onto one side, the f and the g on the other, and so we end up with del squared minus mu naught epsilon naught d squared dt squared lambda is equal to minus 2xt times f plus mu naught epsilon naught g. Okay, you notice the left-hand side, that's just the de-Lambertian, or that block square that we talked about. Okay, so we're just going to solve this by inspection. So what, when you take spatial derivatives, gives you x times t, and what when you take two time derivatives gives you x times t. So we want x cubed times t will satisfy the spatial part, and t cubed times x will satisfy the time part. Okay, so we're going to try lambda equals h t cubed x plus j t x cubed. We'll plug it in and solve for h and j, and if we get stuff that works, then we know we did it correctly. Okay, so plugging that in on the left-hand side, del squared kills the first term and gives us 6, when we take our two derivatives, j t x, and then minus mu naught epsilon naught times 6 h tx, and this is equal to minus 2xt times f plus mu naught epsilon naught g. Okay, so I mean the solution is not unique. We have lots of choices we could use, but just to keep the unit simple, let's just match this term with this term, and so that gives us j is equal to minus 1/3 f. And then when we match the other terms, we get h is equal to 1/3 g. Okay, so then lambda, just plugging those back in, is equal to 1/3. So we have the g times t cubed x minus f t x cubed. Okay, so that's our lambda. Okay, so that's step one. We found lambda. Now the next step is to plug that back in and get our v prime and our a prime. So v prime, by definition, is always going to be v minus d lambda dt. So that's going to be our initial v is gxt squared, and then we take our time derivative of our lambda. That gives us minus g t squared x plus 1/3 f x cubed. Okay, you notice the first two terms cancel, and so v prime is equal to 1/3 f x cubed. So there we go. Now we need a prime is equal to always a plus grad lambda. So in this case, that's equal to a, which is f t x squared x hat. And then when we add the grad lambda, that gives us from the first term plus 1/3 g t cubed x hat, and then minus from the second term f t x squared x hat. And so conveniently these terms cancel, and we end up with a prime is equal to 1/3 g t cubed x hat. Okay, so really there we're done. We found our new potentials. These, as long as we've done our math right, will satisfy the Lorentz gauge. And they'll also give us the same E and B as V and A. But just for practice, let's go ahead and check that we do indeed get the same E and B as we do from V and A, the initial V and A. Okay, so check that E equals E prime. Oops. Okay, so E, the way we get that from the potentials, is equal to minus grad V plus dA dt. So this is equal to minus the gradient of vgxt squared plus d by dt of ft x squared x hat. And this gives us minus gt squared plus f x squared, that's an f, times x hat. Okay, so that's E. Now let's calculate E prime. E prime is equal to minus grad V prime plus dA prime dt. So this is equal to minus gradient of 1/3 fx cubed minus d dt of 1/3 g times t cubed x hat. Sorry, I ran out of room there. Okay, that's a 1/3 there if you couldn't tell. So we do that. E prime is equal to minus f x squared x hat minus g t squared x hat. Okay, and I'll just say that that's equal to the E we found on the previous slide, and since I've gone past it, you can't look back to check, so we'll just pretend that that worked.